Recording. Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great honor and pleasure to welcome SØREN EILERS from Copenhagen, our key collaborator in graph sister algebras. And today he will tell us about equivariant isomorphisms of quantum length spaces. SØREN, the floor is yours. Take it away.
Thank you. So thank you for the invitation to speak here. I want to talk about some things that are new and some things that are old. And before I start, so let me tell you about my co-authors. So there's some old stuff, which is sort of direct classification. I did this some years ago with Gunnar Restorff from the Faroe Islands, Efra Ruiz from Hawaii, Adam Sørensen, who was in Oslo at the time. He's now back in Odense, and then the more recent work is with Sophie Siggers, who is in Prague at this time, and she's also present here as far as I can see. So and this is important because she will hopefully she will stop me if I say something really stupid. So I actually want to start the talk by a warm-up problem, and this is going to look a little bit funny. So trust me, this is relevant, but I just want to show you a problem which is sort of entirely combinatorial and which is directly relevant for the kinds of things I want to talk about. But you will see no sister algebras, nothing advanced in this kind of discussion. So I'm inspired by the time of year. So we are in the situation where we want to turn back the clock for an hour. This has happened in Europe, and I think it's going to happen many places in the US next weekend.
Next week, yeah.
And so so we're in this exciting piece of time where the time difference is not what it usually is. So I want to consider the situation where I need to put my clock back 1 hour. But it's midnight, and if and I'm not allowed to move the hand backwards. So let's say that my clock is arranged so that I can only move the hand clockwise. Then also my clock is such that if the hand goes across the 12 o'clock, there'll be a noise, a bell or something like this. So also I don't want to take it beyond the 12th time on my clock. So this means that there is this is what this 1 down here is supposed to indicate. There's only one way I can do it. I take the hand and I turn it around from 12 o'clock and I go clockwise until I'm at 11, right? Because I cannot go backwards, and I cannot sort of go twice around, because then I would get a noise and wake up the entire family. This is a very simple mathematical problem with a very simple mathematical answer. There's one way of doing this. So I'm going to make it somewhat more complicated and perhaps also somewhat less realistic. But consider the situation where now I have 2 clocks. So these 2 clocks are somehow connected, they are parallel. But one is visible in my clock, so that's the one to the right, and the other one is perhaps behind a panel or something like that. And now I want to do the same. I want to make sure that the visible hand on my clock, so the one to the right, is moved from 12 to 11. But now I have several ways of doing it, because what happens is if I move the hand on the invisible clock, for instance, I move it here from 12 until 8, then the other hand, there's a mechanism that makes that follow along, right? So when I move the backwards hand, the hidden hand, I also move the visible hand. And then, of course, I have to reach 11, so I have to move it the last 3 hours on the visible part of my clock. And my point here is that now I have more than one way of doing this, right? I can leave the hidden one at noon, and then I can take everything around 11 hours, or I can leave the hidden one at 1, and then I take the visible one ahead 10 hours, and so on. And my claim is that now there's a total of 12 different ways of doing this, right? So, and I'm writing it at this sum, so I'm just adding up ones, but the point is that I indicates how long I move the hidden hand, right? So it starts either at 0 or 1 and 2 and all the way up to 11. And then there's only one way of completing the task, because I have to move, you know, the other hand to 11, no matter where it ended up, right? So this gives me more flexibility, but not a whole lot. But now suppose I have 3 of these, right? So now I have 3 clocks, and it works the way before. The one that's visible to the right, I have to make it end up at 11 o'clock. But the 2 ones to the left, they work the way that if I move the one to the very left, then the 2 next ones will move along. If I move the one in the middle, then only this one and the one to the right will move along. And now my claim is that I have 78 different ways of setting back my clock. Right, because essentially the choices I have to make is that I choose a number that I call I. It's between 0 and 11. That's how much I move the one to the left. And then I choose a number called J. That's a number between I and 11, because the middle hand will have moved when I move the leftmost hand. So I cannot start before I. It has to start at Y and I. So this is why this is the sum from I equals 0 to 11. J equals I to 11 of 1. And of course, I can write this as the sum for I equals 0 to 11 of 12 minus I, right? Because the inner sum, I just need to count how many ones there are. And the number of ones is 11 minus I plus 1, right? So it's 12 minus I. And of course, this sum, if we want to compute the sum, there's a formula for triangular numbers, the one that, you know, Gauss is supposed to have known as a kid, right? But that's for summing just the i's, not the 12 minus i's. But it's important here that we notice that these are exactly the same numbers that you would see, right? So the numbers that I see as I go I equals 0 to 11 of 12 minus I, these are exactly the numbers between 1 and 12 that I'm adding up. So the sum of the numbers from 1 to 12 is 12 times 13 divided by 2. So it's 6 times 13, which is 78. So that also gives you the prime factorization of 78, and we're going to need that in a second, right? So it's 2 times 3 times 13.
Sorry, on behalf of Albert Einstein, may I ask you what is the relative speed of his clocks with respect to each other?
They have exactly the same speed.
Okay, they are
so no funny business here in terms of physics. So,
just checking.
Yes. Okay, so I'm going to stop now, but let's say we have 4 clocks, right? Then it works in the same way. Now I have 3 sums with a 1 in the middle, and doing the computation, I get the number 364. Okay, so this is all a very sort of straightforward problem. But now imagine that we are it's getting a little bit less realistic, right? So first of all, it's very important for me to have as many options for doing this as possible. And maybe, you know, in keeping with the other time of year, maybe we're in a castle, maybe we will live forever, and we're doomed to set back the clock every November for eternity. So we want to have as many choices for doing this as possible, right? So we want to maximize the flexibility or the many ways of the variations that we can do this with. So this is one thing that I want to make you think about. And the other thing is that suppose that there is a mechanism that makes one of the clocks move backwards compared to the previous clock. So let me show you how this works. So this red arrow means now that as I move the leftmost hand, the rightmost hand will move the other way. So in this picture here, I've moved it up to 8, but then the rightmost, it actually went the other way, so it's back at 4. Right? So you can see that this is now turned. And the question is, does this change the combinatorics of the situation? And the answer is no, it doesn't. Because of course, no matter what I do to the leftmost hand, I have to end up at 11 on the rightmost hand. So there's no choices when I've chosen what I do to the left. So just like before, I have 12 options. And actually, this is perhaps less clear, but if I did the same with 3 clocks, the same would happen. Right, so let's assume that now the middle clock goes the other way. So when I move the leftmost one to 8, then the rightmost, the one in the middle ends up at 4. and then I just move it in the ordinary way on the right-hand side. So what is the formula? Well, the formula is more or less the same as before, but the j, since I have this reversion, the j, instead of summing from I to 11, I need to sum from 12 minus I to 11, right? It used to be 8, now it's 4. If it was 6, it's still 6. If it's 1, then it's 11, and so on. But there's a problem, because 12, of course, now I have to be careful if I think of 12 as 0 or as 12, right? Because if I leave the leftmost at 12, then this formula wouldn't work, right? Because then I would sum from j equals 12 minus 0 to 11. So that would be the sum from j equals 12 to 11. That must be 0, right? So I have to do that separately. So this is what I've done. This is the first term is where I leave the leftmost hand in 12th position, but the rest of it will work. And in fact, I get exactly the same number as I did before, namely 78. And the point is more or less that I used to have 12 minus I, but now I have I, and it's the same numbers that I sum, just in the different order. Okay, so this is not terribly interesting, but now something happens. When I go to 4 clocks, actually I can get different sums this way. And the point is that, suppose this is maybe not as red as it should be. So the idea is that it's the connection between the second clock and the third clock is twisted, right? So this means that as I change the leftmost, I turn the leftmost, I turn the second one, then that's just like before. If I end up with the second one, for instance, at 5 o'clock, this now becomes 7 o'clock, right? And then I move this in the ordinary way up to 8 and all the way up. And if I do the computation, you'll see that I get a much larger number this way. Right, so this means, you know, if I'm a vampire who has to do this for eternity, it's a good idea to do this little switch, because it gives me 584 ways of doing this rather than 364. And I don't need you to remember these numbers by heart, but I would like you to remember that the difference, the one that I got out by changing the sign here, is 220. So this number will come back. Okay, I'm done with my introduction. So backstory, and I'm going to use it to motivate some of the things that will happen in a second. But it really, if it made no sense to you, you can sort of forget about it, because I don't really need it for what follows. Okay, now I'm going to tell you about quantum length spaces, and this is really the subject of my talk. So I want to show you how to define the quantum length spaces of Hong and Szymanski. And the idea is that you start with the quantum odd-dimensional spheres of Waxman and Soibelman. And this is sort of a universal C-star algebra given by n elements set 1 up to set n, and then they have to satisfy these relations. And to sort of make sense of these relations, you can let q equals 1. So if you let q equals 1, then you can see this means that the sets will have to commute. They will have to be normal. That's what 2 and 3 tells you. And they sum up the set 1 star, which is the same as set 1 star set 1, set I. They sum up to 1, right? So if there's just one of them, this will be like a unitary. So this is a universal C-star algebra unitary that gives you a circle. If there's 2, then you would have something that sort of the spectrum of this commutative C-star algebra would be the subset of R4, which is, C cross C, which corresponds to the 3-sphere and so on. So you can sort of think of this as a natural way of quantizing an odd-dimensional sphere, and it sort of has to be odd because of the way that it's set up. Now, it's important to point out that this C-star algebra comes with a circle action. It's very easy to see, because if I take a number, I just think of a modulus 1 complex number, I'm calling it zeta, it lives in T. If I just multiply a zeta on all my generators, then that will also satisfy the relations. You can sort of see, looking at the relations, why this is true. So maybe I should do 2, 3, and 4 first, because you can sort of see that if I put in a set on one of these relations, they will just cancel out, just one by the other. But of course, the last one, the first one, sorry, you'll actually get 2 copies of set, right? So you'll get zeta zeta square both places. But that doesn't change anything in terms of, because I could just divide through by it. It's not zero. So this will not change anything. So this means that by universal property of the C-star algebra, that gives me an automorphism of this universal C-star algebra. And this is what I'm going to think of as the canonical circle action.
Sorry, might I jump in for just a second? Yes. Because I think it's worthwhile to mention how to get even dimensional spheres. You see, if you look at this relation over here, you immediately realize that when I is the biggest, there is no J which is bigger. So Z with the biggest index is normal operator. And when it's normal, we have no, you will not kill your C-star algebra by setting itself adjoint. When you lose your circle action, all that remains is a Z2 action, but then just by demanding that the only normal generator is self-adjoint, you get exactly the equation for the Waxman, or maybe not no longer Waxman-Sobelman, but for the even dimensional sphere.
I see.
Yeah. So it's worthwhile to see that these even spheres are lurking behind, and they are very easily visible precisely in this relation.
I see. Okay. Yeah. So I mean, the next question is, of course, if you can do the a quantum length space. So that's the next thing I want to show you. So this may be a little bit harder. So actually, the point here is that I can actually do a sort of a multi-circle action. I can take different numbers of modulus 1 and I can put them on the different generators. And for the same reason as before, these numbers, they will not cancel out in the same way as they did before, but just like before, I will get these numbers out and they will still satisfy the relation. So actually, you can get sort of a multi-circle action, which I don't really need for anything. Oops. You take some coefficients. One is called R, and it's a number which is 2 or more. And then you have a number of secondary coefficients. They're called M1 up to Mn. They have to be prime to R for sort of technical reasons. And then you just use these numbers to look at, to define a specific automorphism on the odd-dimensional sphere. And then the fixed point algebra is what is called the quantum length space. And if you sort of trace through the commutative, the non-quantum version of this, you'll get what usually is called the quantum length space. So this definition is how I'm going to define the quantum length spaces. But you'll see in a second that actually I don't really think of the quantum length spaces a lot this way. So what I'm going to do is I'm going to introduce graph C-star algebras and look at them instead. I feel much more comfortable with that. But this is the definition. And I'm going to, for all that happens today, all my secondary coefficients, the numbers that are called Mi, will have to be prime to the primary coefficient, the one that's called R. But that's actually not necessary. So there's a paper by Brzezinski and Szymanski introducing this, and a more recent work of Gottfriedsen and my co-author Sophie that sort of looks at these C-star algebras and classifies some of them. So you could do more, but I'm going in a different direction. So I want to stick with the classical case of the work of Szymanski. Of course, these are sort of well-known quantum objects that have been around for a long time, almost 20 years, and we know quite a lot about them. Mainly because, and this is the first thing that Hong and Szymanski do, we know that there are graph C-star algebras. So let me say a few words about this. So first of all, what do I mean by graphs? So my graphs, there's one thing I need to say. So there's always a dimension lurking here, right? So the dimension is the number that I'm calling n. This is what defines the dimension of the quantum odd sphere. But the way that it comes in here is really as an index on the m's. And this gives me sort of a notational problem, because if I want to specify what the dimension is that I'm talking about, first of all, the dimension is really 2n minus 1, so it's an odd number. but it's really, you should think of it as the length of this vector of units mod r. But I also want to abbreviate it with m with a bar under. And if I use the abbreviation, you can't see the dimension. So I'm going to sort of be a little bit inconsistent in whether or not I write this out so you can see what the length and hence the dimension is. And sometimes I'm going to have to make it short so it will fit on my screen. Hopefully you can follow what I mean by this, but I'm being a little bit inconsistent in my notation, and I sort of feel I have to. so this is just a warning. Okay, so what do I mean by graph C-star algebras? I'm going to tell you in a second, but first I need to tell you what I mean by graphs. So the graphs that I'm talking about, they are not necessarily finite, but they will always be countable. And the way I would like you to think about them is that as quadruples, there's a set E0, which you should think of as vertices. There's a set E1, which you should think of as edges. And then there's two maps, R and S, which goes from the edges to the vertices. And the R is the range map that to every edge gives you where it starts. And S is the source map, which to every edge gives you where it stops or ends. And then we have to be a little bit careful when we have general graphs. So there's something special about a sink. A sink is a vertex in a graph which has nothing emitting from it. So it's a place where you end up and you cannot leave. And an infinite emitter is something that emits infinitely many edges. And so those are special. We call them singular vertices, and the regular vertices are those that are not singular. And here's a graph that's supposed to have a little bit of each. This infinite, this is supposed to signify an infinite number of vertices, a countably infinite number of vertices. So the vertex you see here to the left is an infinite emitter. It sends infinitely many things out of it. The vertex you see here on the right is a sink. Nothing comes out of it. So these are the singular vertices in my little graph. And the two in the middle, they are regular. They emit something, but only finitely many edges. This is somehow essential. And now the graph C-star algebra is the universal C-star algebra by a bunch of generators and relations that you read off from the graph. And this goes back to Kunz and Krieger and has been sort of refined over the years. But the idea is that you take a projection for every vertex, you take a partial isometry for every edge, you force these to be orthogonal in the appropriate sense, and then you say that if you look at SE star SE, this should give me, so this is the initial projection of the partial isometry that I'm associating to the edge E. That should be the same as the projection of the range of E. And if you do it the other way around, you want the same, but you have only this to be true with less than or equal. And then the most important relation is that if you have a regular vertex, which means that's a finite number of edges coming out, not zero, then when you take the SE stars, this will sum up to PV. So these are the famous Kunz-Krieger relations, and this is a way of defining a C-star algebra based on a graph. And you can do this for any graph. You can actually also do it for graphs that are bigger than countable, but I don't want to do that today.
Sorry, may I jump in again for just a second? This is what I was just proving in Tiestes. I'm very excited about it. So first, this relation looks a little bit awkward if you are not a C-star algebraist, but you can immediately replace it by just writing that SE star times PSE is equal to SE star. By this in turn, which is very nice, you can prove that this is the same as proving this path algebraic relation, which is the following: P at the vertex SE. I'm writing with the mouse, so sorry, this is a bit tricky. So PSE times SE is equal to SE. So the beginning of an edge times the edge is equal to the edge. So these are in fact equivalent.
Yes.
These are in fact equivalent for absolutely any graph, okay? So this is one remark that I think is important. And secondly, you see here you had to assume that these partial isometries have mutually orthogonal ranges. If you are row finite, it means there are no infinite emitters, then in fact, this follows from other axioms.
Yes.
That's,
Yeah, I mean,
I know you know it, it's just from other people in buildings.
Yeah. No, so this, and actually, you know, I have to admit that today most of my graphs will actually be regular, so there's no sinks or infinite emitters, and so in this case you can simplify this as indicated. So also an important thing is that there's a unit for this universal C-star algebra precisely when there's finitely many vertices. It doesn't matter if you have infinitely many edges or not. And the unit is just what you would expect it to be. It's just the sum of all the vertex projections of the finitely many vertices. This will become a unit more or less for the reason you just gave. Okay, so this is what I mean by a graph C-star algebra. And then actually Hong and Szymanski prove that whenever you have a quantum length space, it is a graph C-star algebra. So what they say is that there is a fixed R and M, then there is a graph which is regular, so no infinite emitters, no sinks. It has exactly n vertices, and the quantum length space is then isomorphic to the graph C-star algebra of this specific graph. And I'm not really telling you what this specific graph is. I've told you how many vertices it has, but I haven't told you how many edges it has. And this is because this is somewhat complicated. And I want to explain this to you because it's actually important for what Sophie and I are doing. But let me just point out that, for instance, if your R is 12, then there are four numbers that are primed to 12. On 12, so it's 1, it's 5, it's 7, it's 11. And when you compute the number of edges in these four graphs, you get these numbers that you see below. And you can see the difference between the smallest number and the biggest number is 220, just like in my clock example. And this is not a coincidence. I will explain this in a second. So actually, in order to understand what it is that Hong and Szymanski do, we have to sort of look a little bit more closely at the proof. And what they show is that actually there is a more regular graph behind this. So I'm calling it G 2n-1 Rm. This is my own notation. It has exactly Rn vertices, and it has R times n plus 1 times n over 2. This is sort of triangular number you can recognize there. Edges. And then it actually turns out that this will not define the right C-star algebra, but it will define the right thing you get by taking a corner in this graph C-star algebra. So you take this more regular graph. I'll show you what it looks like in a second. I'm calling it G. So this will give you this graph C-star algebra. And this is somehow too big. So there's a canonical projection, which you get by adding up the canonical projections for some of these vertices. I'll show you in a second. Then you cut down to that corner, and that gives you exactly the right thing. And it's a general fact, I think, proved by Arklint and Ruiz in complete generality, that whenever you have a corner of a graph, a regular graph C-star algebra, it's actually itself a graph C-star algebra. But this is in this particular case, Hong and Szymanski did it by hand, and they did it also a long time before the work of Arklint and Ruiz. So I'll show you how this goes. So I can fairly easily explain to you what this G graph is. At least I can give you the adjacency matrix. So I will take an R by R matrix, which is just this forward cyclic shift, right? So it takes the first vertex and send it to the second vertex and then the second to the third and so on, all the way around. And P is the sum of the vertex projections corresponding to the first vertex of every block. And then the matrix is sort of a block triangular matrix where I just take powers of this S with the coefficients that I get in my data, right? So data is a number R that decides the size of the block, the size of the shift. And then the secondary coefficients, the numbers that I force to be units mod R, they are just sort of put into the matrix this way. So maybe you can sort of imagine, right? The first corner, the 1-1 component of this block matrix is just a cycle, And the next one is just another cycle and another cycle. And then you have sort of arrows going across. So this is a lot like Piotr's talk last week, because we're sort of seeing that all the, I mean, it's a little bit different because we're allowing loops, but all the other arrows, they have to move forward all the time. And in fact, a lot like in Piotr's talk, we're also going to count these paths in specific ways. So I don't know if there's a very precise relation, but I wouldn't be too surprised, because actually the combinatorics of this is a little bit tricky, and I'm not entirely sure that we have the best way of doing it. So maybe there's something to look at here. But let me just give you a drawing, right? Because these are graphs, so I should be able to draw them. So I've chosen R to be 4, and I've chosen the dimension to be 3. This means I have 2 cycles. And then they're connected in these ways. And what you see in black, these are the vertices that give me the projections that I'm calling P. And I sort of have a little bit of a tricky issue here when I'm trying to draw these things. So, I mean, these are fairly simple-minded graphs, but there's lots of arrows going across. So it's very difficult to draw in a readable way. So I decided to make it, I mean, the canonical way is to sort of take the one here to the right and move it so that the black vertex is at 12 o'clock. But then everything else would be sort of would be skewed, and this would make it a little bit difficult to see. So I made the decision to put the black at 9 o'clock rather than 12 o'clock. So really, what you have to do, this is the procedure that's given in the work of Hong and Szymanski, which is much more general, is that when I go down to the corner of this graph algebra, I take the vertices that correspond to the black vertices here. So this is a little graph. This is the one we call L3. This is the big graph. This is the one we call G3. And I have this corner given by these 2 vertex projections that I'm adding up. And the way you compute the little graph given the big graph is you simply count the number of paths that start and end in the black vertices and avoid the black vertices along the way. Right? So my claim is that here I have 4 vertices, 4 edges down here. And this is precisely because I can go 1, 2, 3. Okay, I should show. I can go, this is 1. I can go, this is 2. I can go, this is 3. I can go, this is 4. Right? So there's 4 different ways I can go from a black vertex to a black vertex without from between two different black vertices. There's only one way I can go from this black vertex back to itself. That's just running around on the loop. And just like in my clock problem, I'm not allowed to go around twice, right? Because then I get back to the black one. So I'm just counting paths that start and end in a black vertex and avoid the black vertices along the way. This is why I get this specific graph down here. Now, it's going to be a little bit, my graphs will get bigger and bigger. And it's going to be a little bit hard to draw the compressed graph. So instead, I'll just give you an adjacency matrix for that. Now, the point here is that if I change one of my coefficients here, so for instance, I could let the second one be 3, then the graph looks a lot like it, but it's somewhat different, right? So because of this 3, this means that I'm moving something backwards when I go from one cycle to the other cycle, just like on the clocks with this little red arrow, right? So if you compute what happens, it's going to look like this, right? So what I've done is that the second cycle, it sort of run through in a non-canonical order, right? Because it will sort of go from 0 to 3, then to 2, and then to 1. I'm going through the cycle, which is the multiples of the unit 3 mod 4. But then I sort of, so that will sort of give me something which is not a cycle. But then if I sort of unravel that, then the incoming edges will be changed. So this is I hope I do this right, since it's hard to, it's easy to get this wrong, right? But this is precisely what it's supposed to be. But then when you count the number of paths that you can go from one black vertex back to another black vertex, it's just like before. It's there's one from vertex back to itself, and then there's 4 that go across. And now you can sort of see, I can keep doing this, right? So now my dimension is 5, which means I have 3 cycles. And suppose my secondary components are coefficients are all 1, 1, 1. Then it becomes this messy thing. And when you count the number of paths, then you get the same numbers as before. The only new thing here is 10. And 10 sort of comes up because I need to count how many ways can I start in this black thing here and end in this black thing here. And so I guess I can't mark it, but you see which one, right? So I could go 1, 2, 3. I could go 4, 3, 1, and so on. And there's a total of 10 of these. And if I was to, for instance, change the order in the middle, nothing would happen. I would get exactly the same numbers. But now you can almost guess, right? Suppose I have 4, then actually I will now get different numbers, just like with the clocks. So what happens here is that suppose I have 4 and I go 1, 1, 1, 1, 1. So then I get this matrix here, and the interesting number here is 20. 20 is the number of ways of going from the rightmost black vertex to the leftmost black vertex to the rightmost black vertex. But suppose that I turn this one the other way compared to what I had before, then actually I get more options. I get 24. So the numbers I get differ by 4 if my primary coefficient is 4. And if I do it with 12, then we sort of recover the numbers that I found before, because essentially, avoiding a black vertex, that's a lot like moving the hand across 12 o'clock and so on. So it's not the same problem, but it's combinatorially equivalent to it. So I have 4 units, mod 12, and we already talked about 2 of them, right? So it turns out that it's only important what I do here on the third coefficient. So if I take the third one to be 1, so it's just 1, 1, 1, 1, then I get 364 ways up here. If I take 1, 1, 11, 1, that's exactly, 11 is minus 1, mod 12. So that's exactly the number that I had before, 584. But I actually have 2 other options. If I go 5, I have 476. If I go 7, I get 472. So you can see that when my dimension starts growing and my primary coefficient starts growing, I get more and more options for what the graph describing the quantum length space is. So the question that I'm now asking is, when are quantum length spaces different and when are they the same? And of course, in all these cases that I looked at that were small, I got exactly the same graph, right? So even though I had different coefficients, I got the same graph. So of course I get the same graph C-star algebra. But I haven't really told you what's going to happen here, where these 2 graphs are obviously different, right? I get 24 one place and 20 the other place, but it's not clear if I get the same C-star algebra or not. So in order to answer that question, we have to look a little bit into the classification theory for unital graph C-star algebras, and it turns out that there's a very nice result that you can use here. So let me just introduce some ad hoc notation. So an SL upper triangle SL matrix with positive entries is just an n by n integer matrix. It has ones in the diagonal, it has zeros below the diagonal, and above the diagonal, all its numbers are positive integers. And then I also have so that's SL triangle plus, but I also have SL triangle, and that's the same, but I don't require the numbers to be strictly positive above the diagonal. So you can sort of see that the graphs that I showed you this far, they've had adjacency matrices that come from SL triangle plus, right? So here are some examples. They have ones down the diagonal, 0 below, and non-zero numbers above. And so it turns out that you can classify these without really thinking about K-theory. So things are a little bit easier here. So it's a special case of the classification. We classified all unital graph algebras by K-theory and by moves and so on, but I don't want to dwell too much on this. So in this particular case, suppose that I have graphs E and F. They have adjacency matrices A and B that come of this special form, then the C-star algebras will be isomorphic, precisely if the C-star algebras are stably isomorphic, precisely if the sizes are the same, and I can find U and V that are SL matrices, not necessarily positive, so that if I look at U times A minus 1 times V, I get B minus 1. So this means in particular that it's only possible for quantum length spaces. And here it's important actually that we work only with secondary coefficients that are prime. So this statement is not true anymore, and there's an example given in the work of Gottfriedsen and Siggers. But in my case here, it's only possible for two quantum length spaces to be isomorphic if they have the same dimension and they have the same primary coefficient. But the secondary coefficients can vary, and this is really what I want to talk about. Right? So, for instance, let's look at the case where I had r equals 4, and then I had these two different choices of.
Can I ask you a question?
Yes.
So, what was the primary coefficient? What was the secondary coefficient?
So the primary coefficient is the number I'm calling r, which is sort of tells you which roots of unity you need to work with, and the secondary coefficients are then this vector that sort of describes how I twist the various cycles. So you know, the r is the length of the cycle, and the secondary coefficient is how they're sort of glued together.
And you say the first result only works for you said if the like primary coefficient or something.
So it is possible to find two quantum length spaces in the generalized form of Brzezinski and Szymanski, which are isomorphic even though they have different dimension and different r. But if the secondary coefficients are prime, I mean, something new happens if they're not prime. These cycles can sort of come apart into smaller cycles, and this is why the number is not well defined in the same way as it was before.
So you
but
mean
in
like
this particular case, sorry.
So do you mean like when the M does not satisfy this GCD with R, like
yes,
like the prime?
Yes, exactly. So this is the more general. I mean, this is also a quantum length space, but in the original paper of Hong and Szymanski, they were defined to be prime. This was later then generalized by Brzezinski and Szymanski. It makes perfect sense, and then it's also seen to be a graph algebra, and there's even some classification results in the work of Gottfriedsen and Siggers about this. But you cannot sort of. What I want to do now is I want to ask, I have two quantum length spaces, and I want to know if they're isomorphic, and I want to be able to say right away that the dimension has to be the same and the primary coefficient has to be the same if they're isomorphic. So I'm just talking about what happens when I vary the secondary coefficients. This is what I need for here.
Thanks.
So let's look at these two cases, right? So I had the one with 20 and I have the one with 24. So these are different graphs, but they will give me the same graph C-star algebra as a special case of our result. Because if you just take this matrix here with a 1 in the 1, 3 entry, and you just multiply that on, that's like adding a 4 to the 20. Right? It's really like a row addition. Right? So I take the second row and I add it to the fourth row, and that will take me from 20 to 24. So this explains why I can go from one to the other using these U and V matrices, and then as a corollary of our classification result, the C-star algebras are the same. And actually something similar happens with 12. If I, for instance, compare 1111 with 1171, then the numbers I have is 364 and 742. The difference is 108, and 108 is 9 times 12. So I will simply take the column number 2 and add it to column number 4 9 times. Right, so this also explains why these are the same. But now
sorry. So can you go back? Is this really the identity matrix, the third one?
To the right, yes. I mean, you could do it. You could do it with a column. Oh, sorry. Oh, yes. You could do it with a. I just pointed in the wrong direction, right? So
I mean,
I understand what you're saying.
That's the identity, right?
Right. So in what I have on the right, that's what will implement column additions and column additions and column subtractions, right? And what I have on the right is row additions and row subtractions. So I said something wrong. I said I would add the second column to the fourth column. That's not what I'm doing. I'm actually adding the second row to the first row.
All right.
That's also fine. Right? So,
And then you don't need to do anything with columns, and that's why
exactly,
that's
exactly.
Okay, I'm with
but
you.
more, this is just because my example is so simple. So more complicated. I mean, we have more complicated examples where you have to do things both on.
Yeah, sure.
But my point. Thank you. So my point here is that if I just look at the numbers that had a difference of 220, which was exactly just choosing 1 and 11, you can see that I cannot do this anymore. Right? Because the only thing I can do with these SL matrices is that I can make row additions and column additions. And maybe, I can also make some row subtractions and column subtractions. But the only numbers I have to use is 12 and 78, right? And 78, I did the prime factorization of 78. It's 6 times 13, well, 2 times 3 times 13. So the GCD of 12 and 78 is 6. And 6 does not divide 220. So there's no way I can, so whatever I do to the 1-4 entry, it has to be a multiple of 6, right? So it will not be able, I cannot change it by 220 this way. So this really is why I know that these C-star algebras are different. So you sort of see, I mean, the combinatorics of this is a little bit intricate, but it's fairly straightforward, and it just sort of comes back to which numbers divide what and so on. So a little bit more systematically, we proved in our paper that if 3 divides R, 3 divides 12 and not 4, right? So if 3 divides R, then it actually always happens that if you just take 1, 1, 1, 1 and compare it to 1, 1, minus 1, 1, then they're different. This will not be the same C-star algebra to isomorphism. But if 3 does not divide R, then all of these are actually the same. And then there's sort of a natural concept of a critical dimension. A critical dimension is, you fix R, and then you just ask how big does the dimension of the quantum length space have to be in order to get more than one choice, right? So I'm just saying, if I fix R, then I ask what is the smallest dimension so that I can get 2 different quantum length spaces this way. And it turns out this is something I conjectured based on a computer experiment. I mean, it's very easy to make experiments with this because, just have to ask Maple, is there a GL? Is there a choice of SL matrix?
Yeah.
It's a linear problem. You can solve it with integer. It's like a, integral linear algebra. So I was fairly certain that the critical dimension is 1 more than the smallest divisor of R, which is not 2. So it's a little complicated here, right? But for instance, if we look at 4, right? So what is the smallest divisor of 4, which is not 2? It's 4, right? So the critical dimension is 5. So that's why we don't see 2 different quantum length spaces if the dimension is, I mean, if n is 4, which makes the dimension 7, right? But for instance, if I had a big prime like 17, then I would have to go to a dimension. I mean, n equals 18, and I guess the dimension would be 35. And this was then proved by some students of mine who had to use some fairly heavy lifting combinatorics in order to prove this. Right? So this is something that I knew it was true because I could, check it for up to R equals 50 or something like that. But proving it was actually hard. And you're going to see when I get to the new stuff that we sort of have a parallel situation. Okay, now, so this really is the conclusion of the direct classification problem. And so this is the old stuff. Now I'm getting to the new stuff, which is joined with Sophia. And now we're discussing when 2 quantum length spaces are isomorphic in a circle action preserving way. So that's what I mean by equivariant, as in the title. So suppose I have two quantum length spaces, any dimension, but the secondary coefficients have to be prime. And suppose I already know that they're isomorphic. Then I would like to know if they are equivariantly isomorphic. So I mean, is there an isomorphism between the two C-star algebras which commutes with the gauge action on the two C-star algebras? And the gauge action is the one that I showed you on the Waxman-Seudelman odd-dimensional quantum sphere, because the quantum length spaces is a subset of that. I inherit an action from that. And so I just want to know, it's a very naive question, when can I choose my isomorphisms to preserve the gauge action? And I could also ask, I would actually also like to ask the stabilized version of this, and I have sort of a reason for that, and that is actually, so when I have this statement here in the, which is a special case of the classification result of general units or graph C-star algebras, it's certainly not always true that graph C-star algebras are isomorphic if and only if they're stably isomorphic. This is very far from true. But there's something special about the situation here which makes this happen. And it's a little bit, I can sort of prove it, but I don't really understand it. So I would sort of like to see how that goes over here as well. So there's sort of a stable version of this. And then I would like to come up with some sort of equivalence relation on all the possible tuples, right? So these are tuples of n numbers that are units mod r. And I want to sort of be able to say, by looking at the coefficients here, when I get the same C-star algebra up to stable isomorphism. Up to invariant isomorphism. So this is returning to my clock problem. Really what we're looking at now is the distance traveled by my hand as I change the time. And if the two clocks are parallel, it doesn't matter which of these 12 choices I make. Like this, I sort of start at 12 o'clock, and if I use the inner one, the one that's hidden, and I move that down to 8, then I have to move the other one 3 up. Right? It doesn't really matter if I go to 2, then I have to take the other one 9, and so on. So the distance traveled by my hand is always 11 in this case. But suppose that now this is twisted, then I get different distances traveled, right? So for instance, if I take the inner one and I move it to 8, then actually, I move it to, to 8, then the other one is back at 4. So now I have to move that from 4 to 11, so that's 7. So in total, I've moved things 15 rather than 11. And sometimes, of course, it will be shorter, sometimes it will be longer. On average, it's the same. But this is really, now I really care about how long do I have to move my finger as I move these hands. So, in order to answer this question, of course, the natural thing to do is to say, okay, a graph C-star algebra also has a circle action. It's a canonical circle action. It's called gauge action. I find it exactly the same way. If I just take a number of modulus 1 and I put it on all the partial isometries and I leave all the projections be, then this will also satisfy the relation just by before, because I have SE star SE, then I get a set bar set and it cancels out. So it's very easy to see that I get an action of the circle this way by the universal property of the C-star.
Søren, please allow me to ask you a question here. Why is it called gauge action? Because when I was teaching in Trieste about it, this is a question I got. Why is it called a gauge action?
I don't know. I think a gauge is like, you're supposed to think of something which is round, and it's sort of a valve or something like that. And so it tells you how much the pressure is or something like that. But I really don't know where this comes from.
I think that it may come from the fact that in physics there are several gauge theories and they correspond to different forces of nature, like a weak force, strong force, and the simplest one is electromagnetic force, and this one is described by U1 action. So the circle corresponds to U1.
Okay, that makes a lot of sense. I probably we should all learn a little bit more physics in order to talk about these things.
And
But
for example,
it's not a nice notation also because it's very difficult to spell and pronounce gauge. So, but that's just the way it is.
And for example, for the strong interaction, the corresponding group is SU3.
Ah, okay. So sometimes you have actually a higher dimensional sphere action, right? Yeah. So this will not happen here, but so the actions. I mean, even though we have higher dimensional spheres, the actions are always by one dimensional. So so really, you know, what I want to say here is that it's a natural way of attacking this problem to say, okay, well, the quantum length spaces, they come with an action of the circle and they're graph algebras. And graph algebras comes with actions of the circle. So hopefully these circle actions are related. And this happens to be slightly tricky. So let me say a few things about the general case before I move on to this. So it turns out that whenever you have this canonical gauge action on a graph algebra, then the fixed point algebra, so the elements that are fixed by this action, it turns out to be itself a graph C-star algebra, and it's also an AF algebra, C-star algebra. So this, if you know anything about graph C-star algebras, you will know that the graphs that have no cycles are exactly the ones that define AF algebras. And so you can actually in a very nice way describe this fixed point algebra by taking sort of an infinite number of copies of the graph. So I'm doing it here for the graph that I started out with. So you can sort of see that I'm taking this graph and I'm taking the infinite number of copies of this graph, and I'm taking the vertices and I'm putting them in sort of columns. And then I'm taking all the vertices of the original graph and I'm making them point to the next copy. So so the point is that, you know, this, for instance, this loop that you see up here, this is now gone because instead of having a loop which points from this vertex back to itself, it points from the vertex at time t to the vertex at time t plus 1.
Yeah,
so
there's no loop becomes a horizontal line.
Yeah, I mean, so you can sort of, this is also a very efficient way. It kills all loops because there's no way you can move back in time. So this is why this graph has no loops. And it turns out this is a result of CRISP, that if you take this particular graph, so it's an infinite graph, you take a corner which corresponds to adding up all the vertex projections at time 0. So that's why I'm calling it 1, 0. If you cut down to this corner, then that will give you exactly the fixed point algebra. So,
sorry, I don't understand the preamble of your theorem. I mean, surely it is not true for all graphs that the fixed point C-star subalgebra is a graph C-star algebra. So what is the assumption on E?
it is true.
I mean, fixed point of Teplitz is simply not graph C-star algebra. It's minimal unitization of natural numbers.
So it's a fixed point. I mean, so the fixed point algebra of the Teplitz algebra should follow this. So I mean, so it's a fixed point of all the rotations, right? So it's going to have to be constant on top on the circle. So so it's definitely true for all unital graph algebras, but I don't even think that's necessary. So this is a very general theory that, and for the Teplitz algebra, you would have, you know, like this one and a loop, and so that would give you the fixed point algebra should look like. So
yeah, but we know what it is. I mean, that's something easy. If you take this graph, the Teplitz graph. That's my E. I take its graph C-star algebra. I take the gauge action, I take the fixed points. Okay, that's what I will get. I will get the C-star algebra of minimal unitization of natural numbers, commutative one. I don't know how to, sorry, I said minimization. Alexander, 1 point
Yeah, no,
multiplication, right?
This is consistent. So suppose you draw this in the in this cross set way. So this means you have two vertices where you have the one below is a sink. And
Yes.
you have a sink and you repeat this all the way out. And then you have a regular vertex and you have an arrow going across and one going down. And now when you cross down, you would get an infinite number of these sinks. This will correspond to the vertices of n. And then on top of that, you have the extra vertex that corresponds to the unitization. So this will work exactly as you describe it.
I'm still confused because I will live with the fact that, okay, you get it as a corner, but I'm confused by this part. I mean,
right. Okay. So maybe
this is a graph sister algebra, because I mean this is unital, and you show me an infinite graph with infinitely many vertices. So I'm confused. Sorry.
Oh, I see. Okay. You're right. Yes, it's a corner. It's a corner of a graph sister algebra.
That I'm happy with, but not that it's a graph sister algebra. Okay.
Yes.
Okay. Now we are on the same page.
Yes, I see what you mean.
Because this statement as here is wrong. I mean, it's a corner of a graph sister algebra.
Right. So the way that this works is that, most cases you would stabilize it. So because it's sort of a full corner. So this is why, I'm lying to you guys here. So as you stabilize it, you would sort of continue this out to the left, and now things would match up again. So you're right that you have to interpret this in the right way.
Yeah.
But you're certainly right, it's not a graph algebra, because a graph algebra, if it has to be unital,
Exactly.
it does not have infinitely many ideals this way.
Exactly. Yes. Okay. But now we sorted it out. Yes.
Okay. So I'm glad we fixed this hurdle, because I'm going more in this direction in a second. So okay. So I want to tell you about when two quantum length spaces are isomorphic in an equivariant way. And now I have some good news and some bad news. Right? So the good news is that if you use the definition of the G graph, the more complicated graph, and you think of the quantum length spaces as a corner of that, then this is going to preserve the gauge action. You can just check that the map given by Hong and Szymanski, this will commute with the gauge action. So the quantum length space with the action is the same as the corner with the action. Here I'm using implicitly that the P projection that I'm talking about is a sum of vertex projections, so that's fixed by gamma, right? So this is a fixed projection. So this is the good news, right? So this is sort of step one in the proof of Hong and Szymanski. But the bad news is that then if you want to pass to L, which is the smaller graph, the compressed graph that makes things a lot easier to do computations with, the one that I used before, you can see this is not going to be preserving the gauge action. And the question, I'll show you some pictures in a second, but the problem really is that the way that I defined the little graph based on the big graph was that I counted the number of paths that went from one black vertex to another black vertex. And these paths had varying lengths. And so if you look at the gauge action applied to these paths, this will give you exactly the power of Z corresponding to the length. So I had something which was very long, and now I make it very short. This will not commute with the gauge action. So this is precisely the problem. And actually, it's worse than that. You can prove, there's a very recent paper by Abrams, Ruiz, and Tomford that this is never equivariantly isomorphic to a graph sister algebra. So it's not true that, so it's true that if you have a corner of a nice graph sister algebra, this is going to be a graph sister algebra itself, but not equivariantly so. So this is sort of the bad news. But the good news is that then, at least if you look at the fixed point algebra, the fixed point algebra will actually still be a corner of a graph sister algebra, and we can compute this corner. So I'll show you some pictures in a moment, but essentially you take the big graph, the G graph, you make the infinite number of copies of that, and then you go down to a corner, which is sort of given as the combination of the two things we just did. We look at time 0.
Sorry, there's a question from Alex.
Yes.
Alex, just speak it up. Just why should I read it? I mean, you can speak.
Yeah, sorry, I just didn't want to interrupt the flow. Like, what is the issue? Why this can't be a graph system? Like the example, like the argument.
I mean, so I think that actually most of the time, a corner of a graph C-star algebra is itself a graph C-star algebra equivariantly. So the problem here only happens when you have C-star algebras like this with lots of circles. So the problem is that here, if you have something purely infinite, then I don't think this happens. But really, the point is that, I'll show you a graph in a second. There's no way I can sort of adjust because if I want to make this into a graph C-star algebra, I have to change the gauge action. And when I change the gauge action, then I'm going to have to, it's going to be some sort of discrepancy in these sizes that makes it impossible to be a graph algebra. So but is there maybe also some more like so not an equivariantly, this can be a graph C-star algebra, you say, but like so what, why like do they point some argument like why this can't be? Yes, they do. I don't remember exactly how it goes,
Okay.
but you can do it. I think you can do it with just 2. So corresponding to dimension 3 that I have here, you can find examples. So I'm not really using this result here because essentially this is just sort of a no-go. I don't really need to know that it's not a graph algebra, but it's just that I cannot argue this way. So anyway, so let's move on. So let me just give you an idea of what happens, for instance, with this setting that we already talked about, right? So what I have on the top is the graph that I call G3. And now the graph that we call L3, we just count the number of vertices that goes from the black vertices back to the black vertices. And there's one loop on each, and then there's 4 edges across. And if instead of writing up an adjacency matrix, as I did before, I could sort of write up maybe something you could call a symbolic adjacency matrix, where instead of saying that I have 4 vertices across, I will make a vector which has length 4, and I will write the relative lengths of these original paths, right? So all the paths that I have that go from a black vertex back to a black vertex, they have length 4 because I have to go, across 1, 2, 3, or down, across 1, 2. So they're all 4 here. So what I mean by this matrix below is that from the leftmost black vertex back to itself, there's one vertex and it has weight 4. And across there are 4 vertices and they all have weight 4. And back from the second one to the second one, there's 1 and it has length 4. And then the empty bracket that I have in the 2, 1 position, that just means that there are no edges going from right to left. So this is not very interesting, but if I do the same with 1 and 3, you can see something new happens because the lengths of these paths will vary, right? Sometimes if I go across and here, this has length 2. I go down, 1, 2, this is 4. 1, 2, 3, 4, 5, 6. This is 6. 1, 2, 3, 4. This is 4. So you can see here I get different choices of weights, and this means that this I could sort of write it as a graph algebra in an equivariant way if you would let me tweak the gauge action on the graph, right? So really this will tell me what I need to do. So here I have to make it so that if you multiply by set, over here you multiply by set to the 4. And here I have to multiply by a set to the 2, and set to the 4, and set to the 6, and set to the 4, and so on. Then I would get an equivariant isomorphism which intertwines an action of the circle, but it's not the gauge action. It's another action. It's a homemade action that makes this work. And you sort of do this all the time in graph-Caesar algebra theory, because you want to prove isomorphisms or between graph-Caesar algebras. You very often use the gauge invariant uniqueness theorem. And in the gauge invariant uniqueness theorem, you have to have a gauge action on the target, but it doesn't have to be the gauge action. It could be any gauge action. So you sometimes just change this sort of systematically in proofs. And I could do this here, but it's not the right action, right? This is my point. Okay, so I can actually show you what the fixed point algebra looks like for these two cases, right? So what I did here is that I just took this graph. This is let me go back. This is this graph here, right? It has 8 vertices and 13 edges. Now I just make the cross-set version of this, and this will of course give me infinitely many vertices, right? And then the point is that I have to take the corner which lies underneath the sum of this matrix, of this vertex and this vertex, right? So this is going to be a corner, so this is a unital Caesar algebra, but it's actually not a graph Caesar algebra. So this is why we have to deal with the corner. But it's stably isomorphic to a graph Caesar algebra, and actually it's fairly easy to see the ideal structure of the fixed point algebra. So essentially what I have to do is I have to look at this complicated graph, and then I erase everything that does not start in one of the 2 black vertices, right? So you can just see I have this very complicated thing. I remove everything which is not after a black vertex. Right? So there's even, I mean, this goes on to minus infinity. I've erased this as well. So you can sort of see this is a graph. This gives us a graph Caesar algebra, and this is going to be stably isomorphic to the fixed point algebra. And we can see what the ideal structure is, because down here there's a path which is hereditary. When you enter this path, you can never leave it. So this will give you an ideal. And actually on top of this, there's another thing, which if you sort of remove the lower thing, this is also hereditary. So the total number of ideals in this Caesar algebra is easy to compute. There's a 0 ideal, then there's a minimal one, and then there's one that's bigger. So this is what's going to happen if you choose 4, 1, 1. But suppose you do the same with 1 and 3, right? So if 1 and 3, you just change 2 of the arrows. So this is, what I have over here. So if you do the infinite version of this and you cut down, something different happens. So actually, this time I get 2 minimal ideals, right? Because if we trace this way here, this is hereditary. I cannot leave it. This gives me an ideal. But actually, I get another one which comes from up here. That went down here, and then it sort of continues this way. So now I have 2 ideals. So really, when we started this project, we thought, first of all, surely the quantum length spaces are themselves graph Caesar algebras in an equivariant way, right? This turned out not to be true. We also thought, because I thought I had proved this at the time, that there's a complete classification up to equivariant isomorphism of these particular kinds of graph Caesar algebras. But actually, there's a problem with this, and we had to withdraw it. So, I mean, all the technology that I was going to use fell apart, right? So I have to do a very ad hoc argument here. So this is the joint work with Sophie. And the point is that we can sort of see that if we work here with 1, 1 and 1, 3, then actually we get a different ideal structure. And at least the ideal structure has to be preserved, right? So essentially what I'm saying is that I have these 2 Caesar algebras with gauge actions. They're not graph algebras. But when I look at the fixed point algebra, the fixed point algebra is stably isomorphic to a graph algebra. And that graph algebra I can compute, and I can tell you what the ideal structure is. And for these 2 choices of coefficients, I get different ideal structures. So the Caesar algebras must be different equivariantly, even though they were the same in the direct way. So really, the key result is that when you count the number of minimal ideals in the fixed point algebra, and you just have 2 coefficients, like in this case, then the number of minimal ideals is the GCD of the quotient between M1 and M2, M2 and M1, minus 1. So this is sort of a weird quantity to encounter, and we were very confused about this. But let me show you how it works in some examples. Right. So if my primary coefficient is 4, then I have two units, 1 and 3. And so
sorry, but I don't understand this notation. It is M2/M1.
Here, yeah, oh yeah. So I'm computing mod R, and M1 is a unit mod R. So it has an inverse. So I can divide by it.
Okay.
So I'm really working in set mod R.
Okay.
But what I'm doing is a little bit weird. I take these two units and I take the quotient. This is still a unit, but then I subtract 1. Right? And then I look at what is the GCD of this number with R. So of course, the GCD of a unit with R is 1, but now different things can happen when I subtract 1. Right? So if I start with M2 equals 1, then this fraction is just 1. So I have the GCD between 0 and R. So I mean, maybe you don't usually look at GCDs between 0 and R, but it's clear what it should be. It's R, right? This is the biggest number which divides both R and 0. So all numbers divide 0. So so when I take the fraction R divided by R, this gives me 1. And this is precisely because in this situation here, I get just one ideal down below. But then if I do it with 3, I have now 3 minus 1. This is 2. 2 GCD with 4 is 2. So, and then I take 4 divided by 2. So I get 2 ideals. And if I do the same with 12 and the 4 different units I get here, I get different number of ideals. Sometimes I get 1, I get 3, 2, and 6. But we can see right away that then these C-star algebras cannot be equivariantly isomorphic. Right? So if R equals 12, then for the 4 different choices of units, and it turns out you may as well assume that the first number is 1. I mean, essentially it's the quotient that matters. So the number of ideals varies, and so you can see these C-star algebras are different. But if you take a prime, I mean, I've this far I've used 4 and 12 because I like numbers that are very divisible, but I could also take a prime like 5, right? Then what happens is now I have 4 units mod 5, and if I take the unit 1 and I subtract 1, I get 0. The GCD is 5. The quotient is 1. So I can just get 1 ideal. But for the other 3, 2, 3, and 4, when I subtract 1 from 2, I get 1. The GCD is 1. The quotient is 5. Subtract 1 from 3, I get 2. The GCD is still 1. The quotient is still 5, and so on. So now I have 3 different choices of secondary coefficients that give me the same number of ideals. Right? So here I don't know that whether or not the C-star algebras are the same.
Sorry, there's a question in chat. What about different R's?
Different R's?
Yeah. What about between different R's?
Yeah, so I was wondering, like, if you take R equals 4 and M2 equals 1, and for example, R equals 12 and M2 equals 1.
So the C-star algebra, without gauge actions, the C-star algebras are different if you have different R's.
Ah, okay.
So I may as well assume that the R is the same.
Okay, yeah.
So the point here is that, I've chosen a very low dimension, right? The dimension is just 3, so I have 2 circles. The C-star algebras that I get here are always the same because the number of paths that I'm counting, the 2x2 matrix I get is always 1, R, 0, 1. So of course I get the same C-star algebra all the time. That's just because if I have just 2 clocks, there's no variation. This is essentially what's happening here. But in the equivariant sense, I get more variation, as you can see, right? So in all these 3 cases, I get at least 2 different C-star algebras. And actually, it turns out that in the first case, I get exactly 2. Second case, I get exactly 4. And in the last case, I get exactly 2. So the main result we have is this one. So again, we can only really say something very systematic about the case where n is 2. So 2 C-star algebras, quantum length spaces will be gauge invariantly isomorphic if and only if they're stably gauge invariantly isomorphic, if and only if these numbers, the GCD of the quotient minus 1 up against R is the same as the other number. And to prove this, I mean, it's sort of a very ad hoc result. I'm going to say a little bit about what I know in higher generality, but we can only sort of get by with this because the dimension is small. But 1 implies 2 is clear, right? I'm just stabilizing. 2 implies 3. This is counting ideals, just like I did before. Right? So if you believe the proposition which says that this GCD number counts the number of ideals, then of course, if the C-star algebras are stably isomorphic in a way preserving the stabilized gauge action, then the fixed point algebras must be stably isomorphic, and so they have the same number of ideals.
Sorry,
Yes?
what do you mean by weights of paths?
But weights of paths, yeah. So this is like in my notation here, here where I'm putting the weights on when I make the compressed path, then the weights is the lengths of these paths that were compressed. Right. So the weights, for instance, here is that I have 4 ways of going from a black vertex to a black vertex, and if the coefficients are as they are in this particular case, I get the weight 4 times. But here,
okay, so these are like so for you a weight is like multi-length.
A weight for one edge is the power of Z that I have to put on to make the gauge action, to get the gauge action isomorphism. So these are some numbers that can vary, right? So I have 2, 4, 6, 4 here, and I have 4, 4, 4, 4 here. So what we're to prove that 3 implies 1, we prove that actually the weights that you see are exactly the multiples of this GCD number. And so let me show you how this works in an example, right? So
yeah, but we agreed, am I correct in thinking that weights are strictly related to lengths of these possible paths?
Yes.
Okay.
But I reduce them mod R. So this is important here. So the lengths that I got for this particular graph is 4, 4, 4, 4, but I'm reducing it mod 4. So it's really 0, 0, 0, 0. And the GCD in this case was also 0. So really, so the GCD here was 4, right? Because it was a GCD of 0 and 4, which is 4, but 4 mod 4 is 0. So the GCD is 0. So what I'm just saying here is that if the GCD is 0, then the weights I will get will just be 0 4 times. If the GCD is 2, then I will alternate between 0 and 2, as I do here, right? So mod 4, what we see here is 2, 0, 2, 0. So I get, 2, 0, 2, 0, and this will always happen. So this just means that the weights that you encounter are the same. They're sort of predictable when you know the GCD number, but you only know it mod R. Right? So what we were very confused about for a long time is that, does it matter if you have a 6 here or if you have a 2? And that turns out not to matter. So we found concrete isomorphisms. So this is what this is saying. We found sort of concrete isomorphism where we just send generators to generators in a clever way that gives the isomorphism on the nose. So based on this sort of combinatorial information, we can find the isomorphism. This is really what happens here. So we have this sort of quirky lemma. It took us some time to prove it. So I had to ask a colleague. So a good way of proving this is using the Chinese remainder theorem, where you used so the thing that I didn't get in the beginning, you really need to know that the Chinese remainder theorem is not just an isomorphism of groups, it's an isomorphism of rings. So it will keep track of this -1 that you have to deal with here. So the point is that, the numbers that I encounter in this GCD thing is exactly the GCD between a unit -1 and R. So the numbers that you see, of course, you can see they will divide R, right? But you can actually prove that it's exactly the divisors of R, which are even if R is even. So this is what this means over here, right? So if R is 12, then D cannot be 1. And this corresponds to the fact that, the number of ideals that I found for R equals 12 was exactly 1, 2, what was it? 3, 4, and 6, right? Is that right? So the point is that I could never get I could never get 12 ideals, even though 1 divides 12, right? Because I have to find an even divisor of 12. But using this little thing, it's very easy to see that if you sort of define the equivariant critical dimension, it's always 2, right? So no matter what your R is, unless it's 2, right? Because if R is 2, there's only 1 unit, so there's no choice at all, even in the combinatoric. So, then the critical dimension would be infinity or whatever. But otherwise, it's always 2, right? So this is a surprise to me. So very differently from the other situation where you sort of, depending on the size of the R, you have to make your dimension smaller or bigger in order to get different C-star algebras. If you throw in the gauge action, it always happens at 2 cycles, which corresponds to the dimension, the odd dimension is 3. Okay, so I'm almost done. So let me say a few closing remarks. So I mean, this maybe I should say this of course is a very sort of low dimensional result. It's surprisingly complicated that you have to look at this GCD up against R. This gives some surprising, I mean, this confuses for a very long time, but in a sense, it's fairly easy to prove when you sort of have the right way of saying it. And now, of course, you would like to ask, what happens at higher dimensions, right? If I have 3 coefficients or 4 or 5, and I'm a little bit afraid of that problem. I might as well tell you, but let me say a few thoughts about it. And actually, based on, I mean, my thoughts about it are based on this conjecture, which is the idea that you can classify graph C-star algebras, let's say units of graph C-star algebras, up to equivariant isomorphism using the dimension triple. So this is very closely related to the idea of a shift equivalence of shifts of finite type. This is something that was developed by Krieger around the same time as the definition of the Kunz-Krieger C-star algebras. Actually, Krieger's paper is just before the Kunz-Krieger paper in this copy of Inventions from 80. So the idea is that you take this AF algebra that we were talking about, which is also a graph algebra. It's an AF algebra, so its K-theory is a dimension group. And so we call it the dimension triple. It consists on the K-theory of the K0 of this C-star algebra, the order on that K group, and a shift map, right? Because since I have this everything repeated, I can move things either to the right or the left. This will induce a map on the C-star algebra, and that induces a map on the dimension group. So this is called the dimension triple. This is the standard notion in symbolic dynamics introduced by Krieger. Now, the conjecture is that if you want to classify units of graph algebras up to equivariant isomorphism, you take the dimension triple and you throw in the class of the unit of that particular unit at time 0 that we talked about before. And the reason why I'm saying this is a bold conjecture is that we don't know this is true. I mean, essentially we can prove it. And when I say we, it's essentially an old paper of Bradley and Kishimoto, that if your E and F define simple Kunz-Krieger algebras, then it's true. And in the more general case where you have ideals or infinite emitters or sinks, I've looked many places for counterexamples and I haven't found any, but the evidence that this is true is fairly thin. Nevertheless, that's my conjecture. And I think it's also Efren, so I put his name on it. Now I'm going to be even more crazy. And suppose I have 2 unitary graph algebras and I look at corners of those.
Sorry to interrupt you again, but I'm really confused by this notation. What do you mean by the class of something with subscript 0, superscript 0?
This is a projection in the C-star algebra, so it defines a K0 class.
Okay, so just take K0 class of this particular projection. Yes. And this superscript 0, can you remind me again what it refers to?
Yes, so let me go back. So oops. So I had this 1, 0 here, This is just taking the unit of the C-star algebra corresponding to the sum of all these and looking at the copy at time 0. But now I have a corner, which is given by vertical projection. So I'm taking just a subset of some of these vertices, and I'm looking at them at time 0. So, I mean, the point is that this makes sense whenever I have, so we know that there's a difference between looking at a graph algebra as a C-star algebra with a gauge action, with a circle action, and looking at a corner of a graph algebra with a circle action. Right, so now I want to look at corners just like what I did before. And my very bold conjecture, so I didn't put a name on it, but I'll claim it. And I don't know if anybody else believes it, but that would be, that it's true even for corners. You just have to replace the class of the unit that you're looking at by the class of P or Q respectively. So, I mean, this is a little bit technical, but the point is that I really need this shift map. And the shift map only makes sense in these doubly infinite number of copies of the graph, right? Because I need to be able to shift everything to the left or the right. So the dimension group comes with a shift, but this is sort of too big. And I have to look at the corner of this, and this is precisely what this class of the unit or the class of the corner projection looks like. So the evidence for this to be true is very, very, very thin, but it's true here, right? So we have checked that if we do it for the thing that I just told you, it works out, right? So if you take the dimension group in this particular situation and the class of the relevant projection, then they will be isomorphic in the appropriate way. This means, there's a group, there's an order. So I'm talking about a positive isomorphism. It has to commute with the shift, and it has to send the class of P to the class of Q. Right. So this is what I have to look at. And then by sort of going through, I mean, it's very easy here because the group here is set to the 2R. So it's a very, I mean, as a group, and the way it's ordered is very simple-minded. So you can just go in and check that this works out. So this is a theorem in this particular case, and it supports my wild conjecture, right? But the point is now that if you believe my wild conjecture, this is a way of addressing the question of what happens as higher dimensions. Because it's very easy to throw this into Maple and ask, is there an isomorphism between these things? So it's very easy to check this condition over here. This is a computable condition. And so we did this, right? So we, just like in the original case where I had these 3 students prove that I was correct, I'm now in a situation where I can generate a lot of statements based on, no thinking, just computations. And then, of course, the task for me and Sophie is to prove this. So let me, for instance, share what I think is true if you have 3 coefficients. Right? So if you have, so clearly something new happens if you believe the conjecture. So what you have to do is now, I fix, let my prime coefficient be a prime. So instead of R, I'm calling it P. And now the condition is supposing that these 3 secondary coefficients are different numbers. It is the condition that we had before. Supposing that we have repetition, we only get the same C-star algebra if we have the exact same 3 numbers. This is what the computer experiment shows. I have no idea how to prove this, but it seems to be true for all R that 1 implies 2. So no matter, I mean, I've tried this with R up to 30 or something like that. And I tried all the various choices of M1, M2, and M3. I mean, they're not that many. And if you believe that the dimension triple with this class of the P is a complete invariant, which of course I don't know, I'm just guessing, then this turns out to be okay. Right? So it looks like 1 implies 2 always. 2 implies 1. I'm conjecturing it's true for primes. It's actually, I think it's also true for numbers that are 2 times primes. But I also know it's false at 15 and 16. So there's something more complicated going on. So I mean, really, it's a good time for me to stop, right? So you can see what's happening now is that based on the idea that isomorphism, that equivariant isomorphism translates to this dimension triple thing, I can do a computer experiment. This will show me, how things are tied together. And then, of course, to prove that this is correct, we will have to somehow come up with extracting the information from the C-star algebras that we have. Like, for instance, coming up with concrete isomorphisms. Sophie is really good at doing this. And so this is a way of proving that you get the same C-star algebra, or, looking at the ideal structure or something more complicated in order to prove that things are different. But this is sort of where we are. And this is really not something I have any strong ideas for how to prove, but I think it's a very interesting structure that happens here. This is somewhat surprising to me. Okay, let me end here. Thank you.
Okay, thank you very much. Yeah, unless you want me to turn the clock, you're over time, so. Okay, questions, anybody?
I have a question. How strong is the assumption for the graph C-star algebra for being simple?
So graph C-star algebra is simple essentially if the underlying graph is connected. Right, so you want to, I mean, ideals, you get an ideal if you have a hereditary subset, which is something you can get into but not out again. This statement is not technically correct because there's various things about sources and infinite emitters that you have to work out. But essentially, being simple, I mean, it's really, it's a connected graph. That's what you.
It's a very weak assumption, yes. In some sense, it's a weak assumption.
That's true, but you can see, I mean, the setting that I have here. Oh, I forgot. There's another thing. So if you have a vertex with just one loop, this is a connected graph. This will, if you work out the relations, this will give you the universal C-star algebra of a unitary. So this is, C of a circle, which is very far from being simple. So really, the question that I answered, which is not the question that you asked, is when is it gauge simple? When are there no gauge invariant ideals, right? So this is somehow, and the gauge invariant ideals, they are precisely the ones that you can sort of see on the combinatorial.
Okay, thank you.
So I agree that this is sort of a mild condition to give you simplicity, but it's very far from what I have here, right? Because my graphs have these little connected loops, and then all the arrows turn forward. So it's very far from connected. I can never come back. So the C-star algebras I look at here, they're first of all, they have lots of non-gauge invariant ideals, and they will also have exactly how many will they have? Something like n gauge invariant ideals, depending on the direction.
Okay, thank you.
Tomek?
Yes, I would like to ask a question about the relationship between this classification, especially in this non-equivariant case, and the non-classification in the classical situation. What are similarities? Where are differences?
You mean the Elliott program and?
No. I'm talking about the classical length spaces.
Of course, yes.
A lot is known. This is one of basic spaces.
Yes. So this is embarrassing. I never really thought about this, and I know that this is what you use K-theory with coefficients for, right? This is an interest or homology with coefficients. It's sort of and Bockstein operations and all these kinds of things.
But the outcome is fairly simple. It's about divisibility.
Yeah. I think it's very different. I mean, I don't know, Sophie, can you help? Have you thought about this? it's a okay.
Yeah, I can say something because I looked into just let me see. So, for example, if you just have the lowest dimension, then we know that they are all the quantum length spaces, they will be isomorphic, but you can't find homomorphic, non-homomorphic length spaces. So see something different in the quantum case. Yeah.
Good.
And also
So
true
the
for higher
quantum
dimensions.
objects are coarser somehow. They see less.
Yep, exactly.
Okay, so it's interesting. My second question would be about this primary number R, which in the classical case it's an order of a fundamental group. Can you see this finite cyclic group of this order acting on something related to the structure of this sister algebra or embedding of this algebra of invariance in the sister algebra of a odd dimensional sphere?
I mean, you sort of see it. I mean, you sort of see it in the graph, right? Because you have these cycles that have exactly length r, so you can sort of
group of automorphisms of something.
Yeah, I mean, it's defined. I mean, so the definition. I didn't spend a lot of time on it, but the definition, the way they define it, they take exactly a root of unity of order r, and then they sort of they take the fixed point of the gauge action associated, or the circle, the multi-circle action corresponding to the various tuples or powers of this. So you can sort of see it in the definition and also in the graph, but I have to admit it's a little bit, you sort of lose the topology here, it seems. It becomes just combinatorics.
But classically, you know, the odd dimensional sphere is a universal covering space of the length space. And then the automorphism of this covering is this fundamental group. So in this non-commutative setting, it should be automorphism group of this extension. You have this invariant subalgebra and you have this sphere, sister algebra. And so it's a candidate for an abstract definition of this group. Of course, if you think about roots of unity, then it is related to the presentation of the length space. It's not an abstract definition.
Right.
I would like to see
the order of this lambda thing is exactly r, right? So
yeah. But my question was about the action of this group on anything.
Right.
Could be written in terms of non-commutative relations and generators and relations.
Yeah. No, I understand the question. I'm afraid I don't really know so much about it.
So it's a fascinating subject because length spaces are so fundamental in algebraic topology.
Right.
And they are source of so many important notions, like Reidemeister notion, for instance. Having anything of a non-commutative flavor, but having something common with the classical situation will be fascinating.
Yeah. I mean, I have to admit, you know, I think of it very much as a graph, because this is somehow I feel comfortable with this. But what is amazing to me is that you take these very simple-minded graphs and you ask these very simple-minded questions, and it takes you out in extremely complicated sort of computations, mod R, that, you know, and you know, I need to find a number that's the sum of a progression and is not divisible with this and so on. So I mean, the arithmetic side of this becomes very complicated, and I somehow assume that this is because it reflects something deep. but I have to admit I don't really feel qualified to think about this something deep. So I just do the computation.
Yeah, but if I remember well, you used this non-divisibility as a negative argument.
Yeah. Exactly.
So there might be some relation.
It's essential, right? It's essential
Yes,
for these.
an essential argument. Yeah, I understand it. Maybe the next question could be about this gauge action. You said that to obtain some result, you have to assume that you have to adjust this action.
Yes.
You have to consider not the gauge action, but somehow
and a non-standard circle action.
Yes, no.
Yes.
Which of these non-standard actions are could be considered to be a non-commutative counterpart of some classical actions, some standard action? So I suppose.
So yeah, I don't think I know the answer to this, but it makes sense to me that you somehow you look in the classical case, and you should be able to do the same, and then you'll get some weights, and some of these weights you recover in the non-commutative case, and some of them are honestly non-commutative. This is somehow what you're.
Yes, I would like to understand
the
separation between these classical analogs and completely different.
Yes.
This quantum realm, let's say.
Right. I don't know the answer to that. Maybe Sophie, we should look into this. I think it would be an interesting way of going, but we really haven't tried this. But somehow it has to be. I mean, if you sort of believe that the quantum length spaces are the right quantum objects, then this should somehow also be, something you can deform.
Yes.
Right. But I don't know the answer, but I'm very interested in thinking more about this. Do you know anything, Sophie?
He's unmuted. Hello.
Okay. Well, we can. Well,
Okay.
I don't know. we'll think about it. Thank you, Thomas. So, but I'm afraid I don't have an answer for you. But if we find something, we'll let you know. So
the answer of Sophie of my first question excites me a lot, and yeah, it's very fascinating. Thank you very much.
Thank you.
Well, following Tomek's line of inquiry, let me ask the following naive question. If I remember correctly, correct me if I'm wrong, three-dimensional length spaces are used to show a difference between things that are not homeomorphic but are homotopic, right? Do I remember correctly? So I'm wondering, here you went into isomorphism and equivariant isomorphism. How about saying that some quantum spaces are homotopic or non-homotopic, because these are exactly length spaces that are used to show you an example. Look, these compact house of topological spaces are homotopic, but they are not homeomorphic. So I'm shifting the problem. You're saying that things are isomorphic or very isomorphic, and I'm asking that things are not isomorphic, but they are weakly isomorphic. I mean homotopic. Right. And I'm asking because you cannot just go naively by analogy. A quantum disk, a classical disk is obviously contractible, okay? So it's homotopic to a point. But quantum disk is not contractible. And so turning on Q deformation destroys this homotopy. So I was wondering if there is. I'm not expecting you to give an answer. I'm just pointing in following the line of inquiry initiated by Tomek.
So one thing the one thing I can say, right, is that we have a situation where we have classification, so we can sort of get by with K theory. So we can also get by with KK theory. So you can sort of take in C-star algebraic terms, you sort of get weak isomorphisms. You can trade them in for strong isomorphisms. But yeah, I don't know if that's good enough, but that's somehow that's what we know, right? And of course, this is not the case for the equivariant. I mean, this is what I'm hoping for with this dimension triple. I mean, this is not my idea, right? This goes back to Krieger, and there's also in algebra, there's something called Hasrat's conjecture that sort of does the same for Levitt path algebras. You're asking if they are isomorphic in a graded way, and this is as conjectured by Hasrat. This is exactly captured by this dimension triple. So this is also a way of sort of saying that the equivariant problem is translated into K theory. It's just a different kind of K theory. But there's lots of open questions here.
Tomek Brzezinski, would you like to ask a question?
Sorry, I had to unmute myself. Nice to see you all.
Nice to see you too.
No, I have no questions. It was a beautiful talk. Thank you very much, sir.
Thank you.
It was a very nice talk.
Okay.
And maybe just one comment that it's I mean, those length spaces which are orbifold classically, because they are not smooth, they when they are quantized and they become graph sister algebras, they behave in a much more smooth way in a way. So there is a advantage of looking at this graph sister algebra side of the theory. Yeah. That's all. It's not a question, just a comment.
Yeah, but I remember that. I think this is important because it's also a question of removing singularities by quantization, so to speak. I mean, it's an interesting issue. Yeah, funny things happen when you quantize. I know that it's not directly related, but with Bartek Zieliński, we have a paper showing that you start with a trivial principal bundle, you QD-form it, and it becomes a non-trivial quantum principal bundle. So, I mean, funny things happen with a quantization. You can introduce non-triviality, you can kill it somehow. You have something contractible, it becomes non-contractible. You have something trivial, it becomes non-trivial. You have something singular, it becomes non-singular. So yeah, I mean, many things happen with quantization.
Yeah, more or less for 100 years, we know that some funny things happen with quantization. There are some cards which are alive and dead at the same time. So it's
yeah. Yeah, and we're still having fun with it, yes. Okay, anybody else? Any further questions? Adam?
No, I'm happy. Thank you.
Okay, so I think unless again we want to turn the clock, we are really well over time.
Yeah,
so
sorry about that.
Sorry, no, this is a pleasure. So let's thank SØREN again for a very beautiful talk. Thank you. So let me stop recording now.